The question here is, could you do an example on the calculation of the shear stress in symmetric bending? I'm going to show you how to do this for two different cross sections. One is a T-beam, the other is a sort of a rotated channel. Here are the two sections that I have chosen here. Here's the rotated C channel, and here is the T-beam. Point C is the centroid of these sections. The coordinate axes y and z are placed right at point C. You can see these sections are symmetric about the y-axis but not about the z-axis. We want to calculate the maximum shear stress on the cross-section due to a shear force B that acts like shown in the pictures. You might recall this is the shear formula, right? So this is the formula we're going to be using to calculate the shear stress due to the shear force B. You might also recall that the maximum shear stress occurs on the z-axis, the axis that passes through the centroid of the section. The use of this shear formula requires these parameters B, Q, I, and T. The shear force B is given. We need to calculate y bar, that is the location of the centroid along the y-axis, and the second moment of inertia about the z-axis, I, Z, Z, right? We have done this a few times for sections that are similar to this in other videos, so I will not go into the finer details here, but I will leave the calculations here so you can follow. We also need to calculate little t and q. We will discuss that here. Once we have these parameters, we just have to substitute into this equation and calculate the maximum shear stress. Here are the details of the calculation of the location of the centroid y bar for this rotated C channel. The approach taken here is the approach of the composite sections. So I'll let you follow through. Y bar is calculated to be 126.6 millimeters. Here are the details for the calculation of y bar for the T-beam. Y bar is calculated to be 120.5 millimeters. Here are the details for the calculation of the second moment of inertia for this rotated C section about the z-axis. Once again, we use the approach we normally take for composite sections. So this C section is divided up into three rectangles, and we use this parallel axis theorem in order to calculate the second moment of inertia for the entire cross-section. The second moment of inertia, I, is calculated to be 0.9222 times 10 to the minus 3 meter to the power of 4. Here are the details for the T-beam, and here I is calculated to be 0.648 times 10 to the minus 3 meter to the power of 4. Next, we calculate the value of Q for these sections. We are interested in calculating the maximum shear stress, and we know the maximum shear stress occurs on the z-axis, right? So what do? We cut along the z-axis and separate the cross-section into two parts, the top part and the bottom part, right? So we can either use the top part or the bottom part to calculate Q here, and I have chosen to use the top part in calculating the Q. Once again, we're going to be using the principle of the composite sections. For the C channel, I have divided this into three rectangles. This is rectangle number 1, this is rectangle number 2, this is rectangle number 3. QC then is A1 times Y1 bar plus A2 times Y2 bar plus A3 times Y3 bar. And here A1, A2, A3 are the areas of the subrectangles. Y1 bar, Y2 bar, and Y3 bar are the distances along the y-axis to the centroid from the z-axis. Since areas 2 and 3 are identical, both in area and the distances to the centroid, we could combine these two and call this 2 times A2 times Y bar. A1 is this distance multiplied by that distance, so that's 0.65 times 0.05 in meters. Y1 bar is the distance to this point from this line, right? So that'll be 126.6 millimeter minus 25 millimeters converted to meters. So that's what I have over here. The area of the little rectangle 2 is this distance multiplied by this distance, but this distance is 126.6 minus 50 multiplied by 75 millimeter, right? So that's what I have over here. Y2 bar would be that distance right there, which is 126.6 minus 50 divided by 2. So that's what I have over here. So QC works out to be 3.74 times 10 to the minus 3 meter cube for this rotated C channel. The details are pretty straightforward for the T-beam, and here we divide this top part into two rectangles. This is rectangle number 1, this is rectangle number 2, so QC would be A1 times Y1 bar plus A2 times Y2 bar. So these numbers are pretty easy to follow, so I'll let you follow through. And you get a value of 2.64 times 10 to the minus 3 meter cube for QC for this section. So here's the summary of the relevant parameters. V, of course, is given 20 kilonewton. I for this section, I for this section over here, and QC for the rotated C channel, and QC for the T-beam right here, right? Now we need a value for the little t that shows up in this formula. Little t would be the total width of the cross section on the z-axis of the solid part. All right, so here this plus that is the total width of the solid part, right? And therefore little t here would be t1 plus t2. Since these are equal to each other, and we get 0.15 meter for the little t for this section. And here, of course, it's pretty straightforward. Little t is the width of the beam at this point. So that'll be 100 millimeter or 0.1 meters. That's it. So you got everything we need. All you have to do is to substitute these numbers in this formula. So here are the details for this section. So V is 20 kilonewton, Q is 3.74 times 10 to the minus 3 meter cubed, I is 0.922 times 10 to the minus 3 meter to the power of 4, and T is 0.15 meters. And you can see the units is going to work out to be kilopascal. We ended up having kilonewton per meter squared, right? So that's kilopascal. And the number is 540.7. So in other words, the maximum shear stress on this cross section for a shear force of 20 kilonewton is 540.7 kilopascal. And the maximum shear stress works out to be 814.8 kilopascal for this T-beam.